again. So, of course, we have this AdS CFT duality. So some quantity in the conformal field theory is given by some quantity in the dual description. And one of the main challenges is to establish the dictionary. And that's not obvious. It's not taken. It is by far, it is definitely non-trivial. It's not something that just because you say two theories are dual, it doesn't become obvious how to compute which quantities are mapped to which quantities. Okay? So many quantities are being discovered right now. What exactly is the dual? The entanglement entropy was discovered very recently. What would be the holographic dual? Wilson loops was also discovered. Okay, Wilson loops was a bit shortly after AdS, but actually it was some generalization of Wilson loops. Really, the usual Wilson loops, it was only very recently. Amplitudes only very recently. So this dictionary is quite non-trivial. Some quantities are much more transparent what they should be. For example, the fact that dimensions of operators should be dual to energies of strings, that was pretty clear. It was related to the fact that the AdS global time t was the same as the time in the CFT. So energies of strings that are moving in this space should be identified with dimensions of operators on the CFT. Single strings correspond to single trace, and the trace is a one-dimensional object. It's a product of fields. There is a trace, and you multiply fields, and you have automatically a one-dimensional structure. So a one-dimensional object, which is a string, is very naturally identified with a one-dimensional object, which is a trace, which is a product of fields. And this trace can have some excitations that move on this spin chain in the same way as a string can have some string bumps that move on the string. So everything is also natural. Because we have a closed system, either a closed chain or a closed string, the momenta of these excitations on our one-dimensional object, now we don't need to call it string or spin chain, we can call it some unified one-dimensional object, it's the same. As they go around this one-dimensional object, they acquire a phase which is exponential of momenta times the length. This is the free phase shift acquired by a particle that propagates through a distance L. But as it scatters through each of the other particles, it acquires an S matrix, a phase shift, due to the interaction with everyone else. Now, this looks very innocent. You would almost write down these equations, which are called Witt equations, without too much thinking. But there's something implicit here that we must not forget. We are saying that we take a particle, we scatter it with everyone else, and in practice, this is the same as just scattering in a pairwise way, one at a time. And here we are using integrability. We are using the fact that we know that this theory is integral. Okay, once we do it, we compute the momenta. So this equation quantizes the momenta, and we get some set of momenta Pj. And when we have the momenta, we just sum the energies of the excitations. And for example, for operators with S derivatives, there are S such excitations that are moving in this vacuum of this. We computed the energy on the S matrix at leading order, and then there are corrections. And I told you that, for example, the dispersion, this is how it looks like at any value of the coupling. Okay, very good. So just to make it very explicit, let me give you an example. Imagine you take L equal to S equal to. So L equal to means spin chain has two derivatives, length 2. And S equal to means that there are two derivatives moving here. They don't have much space to move. I mean, it's just a spin chain with two sides. So they can either be one on each side, two on the first side, nothing on the second, and so on. We know what these coefficients are. We know what they are. If we require, it's a primary. Okay? And you can now put L equal to S equal to in those equations here. Put here a 2. Put the product up to 2. Write the 2-bit equations and solve. And you can check that the solution is given by P1 equal minus P2 equal 2 pi over 3. Okay, you can just plug, check that it works. It solves the Beaton-Zatz equation, and then you plug these values into the sum of epsilon of 2 pi over 3 plus epsilon of minus 2 pi over 3. They contribute in the same way, and you can check that you get some anomalous part, which is exactly what we expect, namely lambda over 2 pi squared times the harmonic number of 2, where the harmonic number is the sum of the inverse of the 1 over k from up to S. So it's 1 plus 1 half. So you should get these 3/4 if you do this simple exercise. So just plug and check. So I encourage you to do it if you want to make sure you understand this equation. Okay, very good. So what I want to do, at this point, we already gained a lot, because now what we are saying is that the problem of computing, the solution of the problem is reduced now, due to integrability, to a problem of linear complexity. Now we just have to solve these equations. If you put 3 more derivatives, you just add 3 more equations. not growing exponentially, right? Now, of course you could say, okay, but how did we compute this epsilon and this s? We computed by doing Feynman diagrams, so we did one loop Feynman diagram. We diagonalized the Hamiltonian, and we read off what was s. And then we saw it was integrable, the model. Now how would we do it at two loops? Again, at two loops, we would write a two-loop Hamiltonian, write the wave functions, compute s, and then check that it's integrable, and so on. And then, okay, you could say, okay, I will still have to suffer a bit, compute the Feynman diagrams, then I compute the S matrix. Once I have the S matrix, then indeed I'm done. I just write down these equations, and then I just solve them. Could it be that there is a more powerful technique, where instead of going through the Feynman diagrams, that first renormalize the operators, then compute an Hamiltonian, from the Hamiltonian you consider a wave function, from wave function you compute S matrix, from S matrix you write with equations, could there be a shortcut that allow me to, using the fact that I'm describing an integrable theory, go directly and try to get directly the S matrix? Because after all, this is the physical object. The wave function of the operator, it's not very physical. This is the physical object. So first comment is that for general operators, this S matrix, which is a function of P and K, is in fact a matrix, right? Because now you don't have just derivatives, you have different species of operators. Okay? So it's a matrix S, P, and K with some elements A, B, C, D. Because now we can scatter, we can have a derivative scattering with some X field. Okay. Etc. So this is the first comment. And the second comment is, of course, that this S hat is not only a matrix, but of course it depends on the coupling. So it's a matrix that depends on the coupling. Okay, very good. So what I want now to show you, the plan for today is, there are two main computations that I want to show you today. One computation is to show you that indeed, it is not irrealistic to imagine that you could fix this S matrix completely. So I want to show you on a simpler example than this example, which is n equals 4 supreme mules. On a kind of a simpler example, that indeed integrability is so powerful that often you can determine completely the S matrix of your theory without doing any Feynman diagrams, without ever looking at a Lagrangian, without anything. So this is the first thing, is integrability can indeed easily yield S hat directly. Okay. This is the huge gain, then it will be a huge gain. We'll just write an S matrix and have some equations at finite caps. So that's the first thing we want to do. And the second thing is we want to discuss the large spin limit of the Beaton-Zatz equation. What happens when you have many particles? Because then we want to relate this, remember, to the cusp anomalous dimension f of 1. Okay. So this is the plan for today. So we are going to illustrate this by considering a simple example. So the example we are going to consider for illustration is the following. It's an example that is based on the homework that I gave you for today. So today you will be given a homework, and the goal of the homework is to basically fill in some gaps that I will do here rather quickly because as you see, I have to cover 2 points that are not so small. So I'll be going through rather quickly on this example because exactly on your homework you are going to do it in more detail. So suppose we take a relativistic, suppose we have a relativistic. So already by this word, I have a relativistic integrable theory. Okay? Where particles have some index. So let's say we have with O4 symmetry. Okay? So So this index A, B in the S matrix, they run from 1 to 4. So this is a vector index of O4. That is, a particle is not only a particle that moves with some momentum p, but it also has some degree of freedom. It's an arrow that is moving. And this arrow is an O4 vector. Okay, that takes values from 1 up to 4. You can think that particles have 4 colors. They come in blue, red, green, and white. Okay? So this is an example. It's a toy model because here you see you also have different species of particles and so on. So it's kind of a toy model, but a simpler one. For example, relativistic, it's already a deviation from what we have. You see that this dispersion is kind of a funny dispersion. You see, it's not a relativistic dispersion relation. It's not square root of 1 plus p squared. It is if p is very small. Like there is some low energy limit where indeed it looks like relativistic. But it also has a sign which reminds us that there is some kind of spin chain description, that there is some spin chain behind. So it's something in between a spin chain and a relativistic theory. Exactly as it should be. It's some kind of mixture between something that looks more or less relativistic and something that looks like a spin chain. And it's some intermediate object. So this is already not a relativistic model. A relativistic model, the momentum and the energy, they can be parameterized by the so-called rapidity theta. So they have some p and some energy, m cos theta, okay, which is the same as saying that the epsilon is nothing but square root of m squared plus p squared. And we put a pi here for convenience. Okay, theta times pi. Normally you write pi times theta, but I wrote theta before. Okay? So this is a relativistic model. Which model is this? I don't know. But this is a very good definition of a theory. I have a model, it's integrable, it has O4 symmetry. Let's try to see how far we can go without even trying to see what we are solving. Okay, so this is an example for, I just want to stress, this is for illustration, just for illustration. It's not that it is directly related to the model, it's just it illustrates how can we in principle imagine ever fixing an S matrix. Okay, so now we notice that relativistic invariance, okay, relativistic invariance tells us that the S matrix that a priori could depend on theta 1 and theta 2 is actually just a function of theta, which is theta 1 minus theta 2. And the reason you can see is that relativistic invariants that you build out of two particles, like Mandelstam invariant, for example, only depend on theta 1 minus theta 2. Okay? A more physical way of seeing, or a more straightforward way of seeing, is that you might remember when you study special relativity that this theta is kind of a useful parameterization, because if you think for a minute, you see that boosts are just translations in theta. So if it's relativistic invariant, it must be invariant under shifts of theta, so it can only depend on the difference of theta. Okay? So we can see this by notice that Lorentz boosts are equivalent to theta go to theta plus delta theta. Okay, very good. So this is already a simplification. It only depends on the difference. Okay. SO4 symmetry, the fact that we have SO4 symmetry, what does it imply? Well, it is just telling you that you know how to put indices properly, that you are not putting things in a crazy way. So now you have a function of theta that has some index A, B, C, D. And this just tells you that you should choose some function, f of theta, times, and then you put S of O4 delta functions, Kronecker delta functions, which are the only things you can write, which are the only invariant tensors. The only objects you have, delta. Okay. So that's SO4 symmetry, just a statement that this is the only thing you can write. Okay, so our problem is reduced to finding the three functions, f, g, and h. Okay, very good. So we are making some progress. Then comes the most powerful, or one of the most powerful constraints at all, which is integrability. Integrability tells us that the scattering of 3 particles is equal to a sequence of 2 body scattering events. But remember, we can shift the wave packets in one direction, or we can shift it in the opposite direction. It was up to us, right, when we were shifting the wave packets, right? Very good. So what this means is that in integrable theory, the scattering of 3 particles can be decomposed into a sequence of 2 body scattering events, and the chronological order by which they happen, it's immaterial. It doesn't matter. This is an equation. This is what is called the Yang-Baxter equation. And you see that you can write it. I mean, you have some indices here, A, B, C. Here you can produce some index D and F, and you sum over the indices. So this is an equation of the form S hat, S hat, S hat, with properly contracted indices equal to S hat, S hat, S hat, which you can work out the indices just by working out the picture. Say this guy here, for example, would be an S matrix that acts on particles 2 and 3. I can indicate where they act by putting this, and it depends only on theta 2 minus theta 3, etc. Is it clear? Okay, so this is one step where I'm going way too fast. So in the exercise, you are asked to look at this picture and try to convert it into an equation, working out the indices correctly, and so on. Very good, but now you see, if you plug this into this equation, it will not work, unless these functions f, h, and theta are very special. Okay? So immediately, okay, this fixes S up to an overall function. If you just multiply this by a function, it can multiply on both sides, so you can never determine the overall normalization by an equation that contains as many s's on one side as in the other, so it should be always up to an overall normalization. So it fixes. Just to give you an example, you get the following. S of theta equal to some unknown function that people call it typically sigma square of theta times, and for example, the first one should be just I theta divided by, okay, this is not meaningful because if I only write one term, it's not very meaningful. So I have to write at least one more term, sorry. Okay. But I don't have the exercise here with me, so I don't know. Okay, but I can more or less guess what it should be. Okay, I mean, something similar, okay, plus similar, a similar expression of theta times the other tensor. Plus the other one. So the relative weight of the different tensors is uniquely fixed. So integrability doesn't tell you what's the scattering of 2 particles against 2 particles, but tells you what's the relative scattering amplitude between different processes. Okay? What's the ratio between a process where you have particle with color red-green going to red-green or red-green going to green-red. The ratio of the 2 processes is uniquely fixed by having this consistency condition coming from integrability. Is it okay? So we start with a matrix that depends on theta 1, theta 2. At this point, we just have to fix a single function. Huge improvement, right? So now let's continue. Integrability is 3. Now we continue and go on. And 4 can be what's called crossing symmetry. And crossing symmetry is the following statement. First, we notice that theta going to theta minus I is equivalent to flipping epsilon to minus epsilon and p to minus p. This is what is called a particle antiparticle transformation. And then we do the following thought experiment. We prepare a non-physical state by saying that we have some state where we sum over all the colors so that the state is invariant under rotation, so it's colorless, like we sum over all possible directions. We have a singlet. And not only it's a singlet, not only we sum over A from 1 to 4, but we also put one particle with theta and one with rapidity theta minus I. Okay? So this object is what we call some spurious state. You can think of this as a pair of particle-antiparticle that are nucleating in the vacuum all the time and that are not physical. You should not be able to observe it. Okay? And then you do the following experiment. You consider a particle that scatters with this spurious state. So it interacts twice. There is S matrix here, S matrix here. But this should be a spurious state, should be the same. You should be able, in the same way that you can move the lines there freely, you should be able also to move this line and say that it just doesn't scatter at all. So now you just get here a bunch of delta functions. So now you get an equation that tells you that S times S equal to just a product of delta functions. Now you plug the solution that we have here, and you see that, okay, luckily, the tensor structure indeed becomes proportional to just a product of delta functions. That's good. But furthermore, now you will get an equation for the overall multiplication factor, because here you have SS and here you have no S. Right? So this must give you some equation for that sigma, and that equation gives you sigma of theta plus I over 2 times sigma of theta minus I over 2 is equal to theta plus I over theta minus I believe. I have to check. No. Theta minus I over 2, theta plus I over 2. Okay? Okay, very good. And now we have to solve this equation. So let me solve it in a slightly different way than what you are asked in the exercise, so that the exercise is not boring. So suppose I plug here theta equal to I over 2. Okay? At theta equal to I over 2, we get from this equation that sigma at I is equal to 0, because the right-hand side is 0. The other option is that sigma at 0 is equal to 0, but that's unphysical, because that would mean that S matrix is 0. You don't want that at a physical value. So therefore, you conclude that at theta equal to I over, from computing this at theta equal I over 2, you compute that sigma of I equal to 0. If you evaluated this at theta equal to minus I over 2, you conclude that sigma of minus I is equal to infinity. That sigma has a pole at minus I. So you start from this, you write that sigma equal to theta minus I over theta plus I times something that you don't know yet. Then you go on and study it at other 2 points. You study it at theta equal to 3I over 2 and theta equal minus 3I over 2. Okay? And by studying at these 2 values, you conclude that sigma of minus 2I equal to 0 and sigma of 2I equal to infinity. Now the opposite. And therefore, you conclude that you should multiply this by theta plus 2I over theta minus 2I. And to check this, you have to use these 2 values. And then you go further to theta 5I over 2 and minus 5I over 2. Okay. And if you do it, you conclude that you get here some other factor, probably something like this. I mean, this is a guess. I didn't work it out in detail. But this is from plus minus 5I over 2. And you go on like this. And at the end, you arrive at an infinite product representation for this sigma, which tells you, so this, at the end of the day, you find some pattern, and you conclude that sigma of theta is equal to the product of theta plus 2ni, product of theta minus 2n plus 1i divided by product theta minus 2ni, product of theta plus 2n plus 1i. So it's a function that has a bunch of poles and zeros in the half integers, and depending on whether it's odd or even, it has a pole or a zero. And these products go all the way to infinity. Okay? Now, if you have some practice with functions in general, you see what is the function that has poles in the semi-infinite line? Does someone know? A function with poles in a semi-infinite line? Yes? Sorry? Gamma function. Very good. So indeed, as you propose, we write a gamma function with these poles, which is something 1 minus theta over 2i. And if you want to have these zeros, you divide by a similar gamma function, 1 plus theta over 2i. And to have these guys, you multiply by two other gamma functions, 1/2 plus theta over 2i, gamma 1/2 minus theta over 2i. Looks quite non-trivial. This is the full S matrix of our quantum field theory. Okay. There were some assumptions here, but I more or less hid them in the fact that I'm more or less claiming that the solution to this equation is unique. Of course, it's not. It could have extra singularities. So this is what is called the minimal solution. It's the one that contains the smallest number of singularities. So only the ones that I'm obliged to have. You see, I started seeing I need to have some zeros and some poles and so on, and I found the minimum set. I can always multiply this by some tangent or something that will introduce new poles and theta and zeros, but it will be new singularities. So this is the simplest, if you want, integrable quantum field theory with O4 symmetry. Okay? So you see the power of this kind of method of using this kind of these ideas. So this is what is called the bootstrap program. The name is similar to the bootstrap for correlation functions in a CFT, and indeed it has some similarities. Okay? So let me just comment. So we fixed S of theta, okay, without even knowing the Lagrangian. Okay? But then immediately we are left to say, so we don't know what we solved. Right? So we don't even know which theory we solved. And okay, you might be sad or you might be happy. Depends on the point of view. If you want to solve a very particular theory, okay, then it's better. I mean, you wish, did I choose the right solution of this crossing equation? Is this the right solution? Did I really solve what I wanted to solve? Then you need to do checks. Okay? Then we need to do checks. So we can. And what does it mean by doing checks? Compare with standard methods. Compare with perturbation theory, etc. That's one thing we can do. But sometimes we don't even have a Lagrangian formulation. We just say that we have some theory which has some symmetry, there are some particles, it's an integrable theory. Then who cares about the Lagrangian? A priori, the Lagrangian is not something physical. What you measure is energy of particles and scattering of particles. So if you want, the fundamental definition of an integrable theory is a theory where you give me a dispersion and you give me an S matrix that obeys all the constraints that it should. So if it obeys Young-Baxter, if it's unitary, if it's crossing invariant, and so on, it's a good theory. Exactly in the same way as if we solve the bootstrap equations for a conformal field theory. We said this is a definition of a conformal field theory. It's a set of CFT data, delta and C's, that obey some equations. Of course, if you solve, then to ask, which Lagrangian did I solve exactly? What was the theory I solved exactly? Well, I mean, that's always a tricky question. You have some guesses, and then you do checks, and so on. Or sometimes you don't even care. Sometimes you are happy with just being able to go directly to a physical solution in terms of physical observables and jumping all this Lagrangian stuff. But in this case, we know we actually know which theory it is. It is the so-called O4 sigma model that actually describes a vector n that depends on sigma and tau. It's a two-dimensional quantum field theory, which lives in a sphere. Now, let's see, in a three-sphere. So it is just very simple. The Lagrangian is just, there is some tension, square root lambda over 2 pi, integral d sigma, d tau, and then we have some kinetic term. And then we have a Lagrange multiplier that just ensures that the field is in the sphere, where this n is equal to n1, n2, n3, n4. This is a strongly coupled theory. It would be very hard to solve it without using the powerful techniques of integrability, because it's strongly coupled. I mean, just doing diagrams and so on would be almost hopeless. And this is its exact solution for its S matrix. And now you can compute its spectrum using bit equations and so on. Well, let me just conclude because I finished this point. So what I just showed you is that it is therefore not unthinkable to imagine that people could indeed solve this problem in n=4. Now what will change? You will have a different integrable theory. You have a different dispersion. What you call by particle, antiparticle, it's something else. It's a different transformation that flips this sign of this square root. So you choose the parameterization. You work out what's the analog of this particle, antiparticle transformation. The tensors you write, because it's not SO4 symmetry, but some bigger symmetry, are also different tensors. But otherwise, you follow more or less the same strategy. And because you see the dispersion contains lambda, lambda will be automatically built in these crossing relations. So the full solution will also depend on this parameter lambda because it appears in the dispersion relation. And in this way, you arrive at this function S of lambda and P and K that is not. I just want to show you it doesn't look like something out of this world. Technically, it would be something that we could easily do if we had 1 or 2 more lectures. It's not technically more complicated than the kind of things we have been doing. Okay, very good. So this concludes this side of the story of how can we imagine computing the full spectrum of a 4-dimensional gauge theory. But there was a question.
So if I understand correctly, this solution doesn't necessarily solve the beta lambda equation then?
No, this is unrelated. So this,
I mean, if you would apply the same method, because you say it's a solution and not necessarily.
Right. So, but the bit equations are not equations for the S matrix. So this is an equation that determines what is the scattering of 2 particles. Okay. So this is just how does 2 particles scatter. So it's an infinite volume observable. You have 2 particles, you scatter them, and you get some S matrix. Once you have some S matrix, once you compute, you write down bit equations. And bit equations are not equations for the S matrix, they're equations for the momenta. Right? So now that you have this S matrix, you could plug the S matrix here that we computed. For P, use the P for m cos theta, use this S matrix as function of theta, and you get a new set of bit equations. They look different from these ones because they describe a different model. And then you compute you quantize these thetas, and you sum the energies of the thetas, and you get a spectrum of the O4 sigma model.
But do you know if it's the right? So it could be the wrong.
It could be the wrong S matrix. A priori, if I only know, for example, if I only know I want to study this guy, right? Everything goes through, but here there was an assumption. I looked for the solution with a minimal number of singularities. But then you could ask, okay, but if there are other singularities, it means other poles. But poles must be interpreted as bound states when you have poles in an S matrix. So then you can do a semi-classical analysis of this theory. And you can see that in the semi-classical limit, at least there are no bound states. So that's a strong indication that you do not want more singularities. And then you hope it's okay. And then you do checks. Okay? And there's absolutely no doubt that this is okay. Okay, very good. So then we finish the first half. Okay? We go to the second half, where I just want to show you what the result is. I mean, here I really have no other option. So now the question is, okay, we have an S matrix, we have a dispersion, we have some bit equations. And we now want to complete the plot and find the plot for the cusp anomalous dimension as function of the coupling that we know the beginning, we know the end, and the goal is to find this full curve. So what do we have to do? We have to compute the dimension when the spin is very large, and we get some function f of lambda times logarithm of the spin, and this is what we want to compute. So we want to consider a spin chain with many particles. Okay? So what do we do? Well, first of all, the right description to describe many particles is to replace this momentum p by some density of momentum p. You will replace products appearing in your bit equations. You replace them by exponentials of sums, of logs, of whatever was here. And this you will replace by exponential of integral of some density times some kernel. And you will find integral equations for this row. Okay? Okay? And then this, you get integral equations schematically of the form identity plus some kernel acting on rho equal to some source. Again, I'm being very schematical just to illustrate. There are some integral equations. This means convolution. And then what you do is you invert whatever kernels you get. Typically, to invert the kernels, you go to Fourier. And because you go to Fourier, you will see some expressions that you maybe don't recognize because it's the Fourier transforms of the kind of S matrices and so on that we wrote before. And then, once we invert, we compute the cusp dimension f of lambda, which will be some functional of the solution to this equation. Okay? So in principle, it's not a very complicated problem. It's just, this is the equation, take the large S limit of this equation. I'm just telling you that, as usual, we replace sums by integrals, blah, blah. It's nothing very special. Okay? So the solution that I'm now going to write for what's the final result, you will see some kernel, you will see some inversion, you will see some coupling appearing there because S matrix appears on coupling, but otherwise you will not recognize it as anything that we have seen before because there are many steps on the way. Okay? So I just want to write here what's the full solution for this F. Okay, so first we construct a matrix. Okay, so here is the solution. Okay? This is again using integrability. It's a method that is not using weak coupling or strong coupling, it's using this kind of integrability. Then we are going to plot this solution and check whether it matches with weak and strong coupling, and this will be evidence for AdS CFT. Because we will have a totally independent solution and then track it. It interpolates perfectly between weak and strong coupling. So here is the solution from integrability. So you first construct a matrix K, which is a matrix Kij, which is given by twice minus 1 to the I times j plus 1 times j. So far, it's not a very complicated matrix. And then you have integral from 0 to infinity dt over t e to the t minus 1. And then you have Bessel function j with argument I and argument 2gt, Bessel function j with argument 2gt. So these are what kind of expressions appear when you Fourier transform the S matrix and so on. Where I'm using a parameterization of the 't coupling, which is quite convenient, where square root lambda over 4 pi is defined as g. Just useful parameterization. Okay, this is the first step. let me check if I did any mistake. Probably I did. Yes, I did. Okay. So this is J and this is I. But okay, who cares? It's just to illustrate how the solution looks like. This is first step. Okay? Then you construct the matrix delta ij plus kij. Okay? So you construct this matrix. And you consider this matrix, okay, where I runs from 1 in principle to infinity, but we put a cutoff, j. Okay? And we will take the limit when this cutoff goes to infinity. So the bigger the matrix we consider, the best our plot will be. In practice, lambda equal 10 is perfect for the human eye. So in practice for us, lambda is equal to 10. Once we compute this object, we take the inverse. This comes from inverting these kernels to find the solution row. We take the inverse of this matrix. And then we take the element 1, 1 of this matrix. Okay? So this matrix, it will contain the cusp anomalous dimension in the first element and then stuff that we don't care in the other elements. Okay? So this is the full solution for the cusp anomalous dimension. Okay? It's not. I forgot something. There is lambda over 2 pi squared here. Now it is the full solution. Okay? So zero order check. Let's see what happens when lambda is equal to 0. Okay? So pay attention, see if you understand this part. Lambda equal to 0. Bessel functions are 0 at the origin. So k is 0. Okay? K is 0, so we have to invert the identity matrix because k is 0. But identity matrix is very easy to invert. It's the identity matrix again. What's the element 1, 1 of the identity matrix? It's 1. So we see that the cusp dimension is lambda over 2 pi squared. And that was the leading behavior indeed. We were saying that to leading order, we have just lambda over 2 pi squared. Okay? Very good. Otherwise, this is the computation. So now we implement this in Mathematica. Oh, wow, we have lots of time. Very good. So now we implement this in Mathematica. So I need the computer. Any question while the screen goes down? Can someone put the screen down? I don't know how to do it. Very good. Thank you. Any question? Do you want to ask something about the full solution? Do you agree that it doesn't sound totally insane that something like this could appear, right? From the kind of procedure that I said. Okay, so let me first okay. Can you see? No, not yet. Okay, should I change something? Is it PC, HDMI, RGB? Which one is it? Maybe RGB? Let's see. Good. Okay. So, is this zoom big enough? Oh, very good. So here, I just prepared the weak and strong coupling result. So you remember, weak coupling was this lambda over 2 pi squared minus lambda squared over 96, blah, 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 blah. And strong coupling starts square root lambda over pi, minus, and then some corrections. Very good. So now we will compute our matrix K. Okay? K of G. So okay, first of all, let me use some notebook kernel. Compute 5. Okay. So I'm using some cluster so that the computation we're going to do of this matrix can be sped up a bit. Okay, very good. So now the computation is not running on my computer. Okay, so we have some kernel, and what will this be? It will be a table of integrals, and integrate, and we will integrate something from t equals 0 to infinity, right? But infinity is kind of annoying to do numerics, so we just choose infinity to be 200, which is more than enough. Then we can check that if we change this inf to another number, the numbers don't change. So it's just a cutoff so that we don't integrate all the way to infinity. And then we will construct a matrix from I up to lambda and from j up to lambda. But again, lambda will be some big number. And for us, lambda equal 10 is more than enough. Okay? And then what do we integrate? We integrate 2 times minus 1 to the j I plus 1 times j. And then this Bessel function. So Bessel j of I to gt. Okay, and Bessel j of j to gt, and this is to be divided by t times e to the t minus 1. Okay? Once we compute this value once, we can save it if we want, so this saves time if we want to ask for this matrix once and then keep it. So we can compute dsk of some value. Now, one thing I'm going to do is instead of table, I'm going to put parallel table so that Mathematica computes these different i's and j's using different kernels, so that's a bit faster. So, for example, you can ask, what is it when the coupling is 1 over 100? So the slow part is just to launch the kernels, but it only will do it once. There are 16 kernels, so it takes some time. And then it will be rather fast. Okay, and it gives us some matrix. So here is some matrix. And you see that it's indeed good to cut off, because you see these numbers are already very small, 10 to the minus 22. Only the ones close to the corner are reasonably small. You see? 0 point, blah, blah, blah. Is it clear? So if you ask, let's just ask for matrix form. You see, the ones close to the upper left corner are reasonably small. These ones here, 10 to the minus 34, they are starting to become very small, even for very small coupling. Okay, or especially for very small coupling. Okay? So we can see this very clear if we do just some matrix plot. Then we can see very well. Okay? Okay, very good. So the cutoff is more than enough. Then what do? We define some function, f of g, the cusp anomalous dimension. We are using g instead of lambda. So this lambda over 2 pi square is nothing but 8g square. Okay? And then what is it? It's the inverse of the matrix, which is the identity matrix of dimension delta, plus this matrix K of G. And then we take the inverse of this matrix and take element 1, 1. Okay? So we ask, what's the cusp anomalous dimension for the coupling 1 over 100? And this is what it is. Okay? And now what do? Well, we make now a plot. So we ask for a table of lambda, and the relation between and lambda is 16 pi squared g squared. Just convenient. This is lambda. Okay? Because square root lambda is this over 4 pi. Then we plot f of g. Okay? We make a table from g equal, let's say, a small coupling, up to g equal 1. G equal 1 is already lambda very large, you see, because lambda comes multiplied by 16 pi squared. So g equal 1 is like lambda equal 130 or something like this. It's already very strong coupling. And we do this in steps of, say, 1 over 10, for example. This gives us a table. We list plot this table. When we list plot this table, we can put some point size to be reasonably large so that we can see it. Okay? And And that's it. We can put some monitor to see where it is doing this G computation. G, some, say, okay. And this is our plot, cusp plot. Okay. Okay. So we just plot for several values of G. Okay. And tack. Here is the value. Here is the cusp anomalous dimension for any value of the coupling. Okay. We can do smaller jumps if we want to see more points. And this would be what it is. Okay. So here is the cusp anomalous dimension all the way from lambda equals 0 to lambda equal 140 in a 4D gauge theory. And now let's check whether this sounds good. Let's ask to show the weak coupling, strong coupling, and finite coupling predictions all at the same time. So we ask to see weak, strong, cusp. Cusp is the numerical 1. We can ask to see all in all range. We can ask to put the origin, otherwise she chooses the origin at 0, 0. And we can put some plot label. Plot label, we can say this is cusp anomalous dimension at any coupling and AdS CFT. And we can use some axis label. We can say the first axis is lambda, and the second axis is f of lambda, what we are plotting. And voila. See? The weak and strong coupling results. You see? These are the two curves, the orange line and the red line, and the weak and strong coupling predictions. And the dots are our numerics. And you see that they go straight through each other. Okay. This prediction here, the red one, is using some order in perturbation theory. If I would, for example, use one less order, if I would not use the computation that was computed 2 days ago, for example, right, this last number, then I would ask to plot again. Okay, it would be a bit less good at weak coupling. But okay, they computed, we can use it. And now it's indeed very good. So this is the illustration of how a gauge theory becomes a string theory and how a string theory is becoming a gauge theory. And if you want, this is an illustration of AdS CFT at work. So let me just comment let's conclude just by saying that, of course, this was an exploration course. So the main goal of the topic was to show you some advanced research topics and some exciting developments in the context of AdS CFT. But just we should, of course, keep in mind that AdS CFT is a huge topic. I mean, probably half of the people working on string theory are doing AdS CFT. The AdS CFT original paper has like 8,000 citations. So, of course, this is only a very, very, very small tip of an iceberg of a huge subject that I encourage you to learn more about, both conformal field theory, both string theory, and quantum field theory. And let me conclude with, now you are all going to do your PhDs, with a general advice for your PhD, which is that whenever you are going to choose a topic to work in, it's the time to choose a topic that is very broad and that requires connecting different things. There's always a temptation to start directly working on a problem that you can understand and start solving some differential equations and start doing some simple computations in gravity and starting to get immediately some plots and so on. And then there is the temptation on staying along some problems that are prolific and so on. And try to always keep in mind that the PhD is the time where you can learn some huge subject and get connections between different topics. And then when you will go for your postdoc and future research, you can absorb easily other topics if you have some huge topic. But if you focus too much, then you will have a hard time as your postdoc and as a researcher later of absorbing big bulbs of information. Just because on the one hand you are not trained to do so, on the other hand you will not have 4 years where you can calmly do so. So it's really, whatever you decide to study, try to aim for some big topic. Either some problem scattering amplitude, which is a huge field, or some important development in conformal field theory, try to choose something that is big and that after learning it, that's something that you really need a PhD to learn, not a sequence of small projects that you need 1 week for each of them. Okay, that's my advice. I want to finish with just this general advice. Okay, thank you.